At the end of the last class, we were discussing about estimating the mean response when x is x naught. And we were at a stage where we were trying to find the variance of beta naught hat plus beta 1 hat times x naught. We opened the expression and we came to a stage where we needed the covariance. It was 2 times x naught into covariance of beta naught hat and beta 1 hat here. And this is what became the assignment. How many of you tried it? And of course, you couldn't get 0 because it is not 0. Yes. There is a result in this assignment that is actually 0. I will fill this up later and I will change this assignment a little bit. Let us try to find this one. Let us try to find this one. By definition, what is covariance? I will write it here. Covariance of xy is expected value of x minus the mean of x times y minus the mean of y. This is by definition the covariance. So we write the covariance, this one, to be equal to the expected value of beta naught hat minus the mean of beta naught hat is beta naught times beta 1 hat minus beta 1, where beta naught is the mean of beta naught hat and beta 1 is the mean of beta 1 hat. Right? Now, of beta 1 hat. This is the expected value of beta 1 hat, and this is the expected value of beta naught hat, which we already proved. Now, what I'm going to do is I'm going to put the definition of the intercept, which is y bar minus beta naught, yes. I just put beta naught hat. Clear? Now, in this whole thing, there are no hats on these two things. So I'll distribute it, all the three terms separately. So I will have the expected value of y bar times beta 1 hat minus beta 1 minus beta 1 hat times x bar into beta 1 hat minus beta 1 minus beta naught hat, not hat, beta naught times beta 1 hat minus beta 1. Which one become which? The first one is this into this. The second one is this into this. The third one is this into this. Now, when you apply the expectation on the third one, what will be the result? Beta naught is a constant. It will go out and expectation will be applied on beta 1 hat minus beta 1. So what is the expectation of beta 1 hat? Not 0, beta 1. And what is the expectation of beta 1? The expectation of a constant is the same constant, which is beta 1. So beta 1 minus beta 1 will be 0. The last term will become 0. Now, this is simple. What is the mean of a constant? What is the mean of a constant? If I have a constant 2, the mean of a constant is the same constant, right? That's what we are saying when we take the mean of this constant, the mean will be the same constant. If you take the mean of beta 1 is a constant. It will be the same. Beta 1 hat, the mean of this one is beta 1. So beta 1 minus beta 1 becomes 0. The expectation doesn't become 0.
So beta 1 has the expected value is beta 1.
Yeah. So after 2 or 3 steps, it becomes 0. The expectation doesn't become 0. We're yet to talk about these things. We only talked about this part. And as a whole, when you apply the expectation, this will be minus beta naught times beta 1 minus beta 1. When you do apply the expectation, and this will go to 0. Okay. This is going to get very long. This is going to become beta 1 hat square. And when you apply the expectation of beta 1 hat square, where will it come? This will come from the variance, because by definition, variance is expected value of x square minus expected value of x whole square. Then you use it the other way and get this one from here. Here you will have beta 1 constant, so it will be expected value of beta 1 hat. This will be easy. Here you will have beta 1 constant. The expected value of y bar is mean of y, mean of y, which is mu of y. And here this will be tricky. To do this, I'm going to use some properties of covariance to make it easier. Some properties of covariance. First thing I do is I put the definition of beta naught hat. Then there is a property of covariance that covariance can be distributed for negative and positive sign. So this thing will become covariance of y bar with beta 1 hat minus covariance of beta 1 hat x bar with beta 1 hat. The covariance can be distributed for plus and minus sign. So I distributed the covariance based on this minus sign. This is one thing. Then there is another property of covariance. How does the constant come out of the variance? Square. How does the constant come out of covariance? Without square, just as it is. If this constant is only on one place, it will come out one time. If it is on both places, it will come out square. So this term becomes x bar only one times, and then there is covariance of beta 1 hat with beta 1 hat.
Why?
It's a constant. And this thing stays covariance of y bar with beta 1 hat. Then what is covariance of x with x? Put, where is the definition? Put here, instead of y, put x. What does it become? It becomes variance. So covariance of beta 1 hat with beta 1 hat becomes variance. So it is x bar times variance of beta 1 hat.
Which one are we doing? Beta 1 head and beta not head are the one we are working.
They are constant within sample. Beta 1 hat, beta naught hat, they are constant within sample. Within a sample, these are unique values. So the summation will not be applied on them. Expectation will be applied on them. Just read the two lines. Expectation, variance, covariance, these are applied on overpopulation. Yeah, well, with respect to B1 and beta 1 and beta naught, they are constant. Whether you're talking about sample or you're talking about population, they are constant everywhere.
And the X bar and Y bar always constant.
X bar is constant, Y bar is not constant, because we are assuming X is to be fixed. Fixed. Yes. These operations will not apply on X. This. But this operation will be applied on X. No, not beta hat. Because if I take a sample and I calculate the intercept from that sample, the intercept is a single value. It's not a variable. The intercept of regression line from a given sample, it's a single value, right? Now this single value, when you apply the summation, you will apply the summation over that specific sample. So for that specific samples, beta 1 hat is constant. Yes, because the expected value is overpopulation. So if you change the sample, beta 1 hat changes. So you do apply the expectation variance and the covariance. So we are here. What is variance of beta 1 hat? Now this becomes the assignment. So a little change here, that you have to prove that the covariance between y bar and beta 1 hat, this is 0. Yes. And it is tough. It's not easy. It is tough. And it is not exactly step by step given in the book. There is a hint in the book. There is a hint in the book in section 2.2.4. I suggest to work for it. Of course, it is graded. Yes.
Actually, 26.
26?
We lost one game.
26.
It's tough. So.
Windows 28.
27.
One day, 27.
29.
Without delete.
Alas, 0. As many as you want on the left side. 27. 11:59 p.m. by the end of the day. Okay, when you do put this definition, by the end, we get the covariance to be minus x bar times sigma square over minus x bar times sigma square over sxx. When you put this thing in here, by the way, we were working here in equation 1. This is what we were working for. When you put this thing in here, I will copy this equation as it is. And I will plug the result in here. Copy. We were working for variance of mu hat of y for a given x naught. So I'll put this covariance of beta naught hat and beta 1 hat to be minus x bar times sigma square over sxx. And the things become very simple. One thing I can do is I can take sigma square as a common factor true. From all three of them, there is sigma square, right? Then there is one thing which is 1 over n. This is done. Then from the remaining 3, I can take sxx as a common factor in the denominator because the remaining 3, all of them, they have sxx, right? And then I have x bar square minus 2x bar times x naught plus x naught square, which is a complete square. So the final result comes out to be 1 over n plus x naught minus x bar whole square over sxx. This is the variance. And based on this variance, I can simply design a confidence interval, and the confidence interval will be mu hat of y given x naught plus minus z alpha by 2 into square root of sigma square into 1 over n plus x naught minus x bar whole square over sxx. But I will not do that. Why? Impractical. We don't have sigma square. Same solution. What do we do? This is the confidence interval. For the mean of y when x is x naught. This is what we are going to apply in Excel. This is the final formula that we will apply. Let us apply. So we were dealing with that example 2.1 from the start. Now in that example, we have, what do we have? What is y, what is x? For the propellant, it's the age of the propellant, which is the the predictor variable, and the strength of the propellant is the response variable y. So let us fix the age of a specific propellant for which you want to do the prediction. Suppose we want to see when the age of the propellants is, let us say, 15. Now, one question. In your population, how many propellants are there? Infinite. There are population. There are infinite propellants. How many of them they have age 15? Infinite. There are infinite many propellants which have the age 15. Do they have exact same strength? They have different strength, right? So for x equals 15, there is a complete population of y. The strength of all those propellants which are 15 weeks old, they have different strength and a complete population of y is there. The objective of this question is to estimate the mean of y for x equals 15. All those propellants which are 15 weeks old, we want to find the average strength of those propellants, mu of y when x is 15. So when x is 15, x naught, we put it to be 15. Yes.
X is variable. Can I know the mean of y of all x1, x2, x3, x4?
We did not go into the derivation, but last class I briefly discussed that even if you let go of this assumption of constant and fixed x's, the results don't change. Mathematically, they don't change. So all these results that we are deriving, they are also applicable even if x's are not fixed. Only a little bit of interpretation is changed. You will not talk about fixed x. You will talk about variable x. But mathematically, I don't need to go into the proofs, but they don't change. Same formula for beta naught hat, same formula for beta 1 hat, same formula for the predicted value, same confidence intervals, all the things are same.
Predict the average of y given x is 15, be the same as the average of y for 1 x.
Same. For
x is
all x's? No. In that case, this thing will not make sense. If you think that there is only one propellant, if you are considering x to be a variable and a continuous variable, then there will be only one value 15 in the population. So in that case, this mean thing will not make any sense. The single value will make sense, which we will cover after this one. So what is mean of y when x is 15? The point estimate. What is the point estimate? The point estimate we discussed is what? We just plug the value inside the model and get the point estimate. Mu hat of y when x is x naught is simply what? Beta naught hat plus beta 1 hat times x naught. So I just plug it in, equals, where is my beta naught? This plus this times 15. 2070.51. This is the estimated mean strength of propellants which are 15 weeks old. Mu y, yes. Mu, it's mu hat, not mu. I don't have a symbol of hat in Excel, so it's. So it's the estimated. When I say the word estimated, it's not exact. It's the estimated mean age of all the propellants which are 15 weeks old. Estimated mean age of all the propellants which are 15 weeks old. To get to the confidence interval, what do we need to do? We need to follow this formula. The point estimate plus minus the critical value times MSE into 1 over n plus this. So I'll write this formula now. For the lower limit, I will write the point estimate 2070 point something minus for the critical value T dot inverse. And throughout the course, we will talk about two-sided confidence interval. So whenever I create the confidence interval, it will be a two-sided. So always I will divide alpha by 2. I can use, no problem, because it's the same degrees of freedom I can use. Did I calculate? I didn't, yeah, 2.1009 I can use. Yeah, I can click on critical value times square root of MSE, which is this, times 1 over n plus x naught minus, I think I don't have x bar, right? I forgot to. N is 20. N is 20. So I have x naught minus, I don't have x bar, so I'll just take the average of these x's. And then I have whole square. And then I have sxx. I think I have sxx. This sxx. So this is the lower limit, 2024 point something. Let us try to match it with the result from book. .5. The prediction of new observation, no. The mean response. Here. This one is calculating for x naught to be, what is the value of x naught they are using? What is the value of x naught they are using? Where is x naught?
X bar equals 13.
That's x bar, but where? What is the question about x naught? Where are they?
X naught equals X bar.
Where?
13.
Does it say?
Yes.
Where?
Yes. Here.
Oh, that's a comment. I will come to that comment. But in this example, what is the value of x naught they are using? X naught minus this. If we substitute x naught and the fitted value into this, we obtain, for example, if we, yeah. So let us take this value of x naught and compare our confidence interval. No, I'll substitute it. So the lower limit is 2086. Is it same? Yes, 2086. And the upper limit, I'll copy the same thing with a plus sign. And this will give me the upper limit. Which is 2176. 2176. How do we interpret this interval? The interpretation of this interval is that for all the propellants, now this is very important. In the next section, I'll be talking about the single propellant, but this section is about all the propellants whose age is 15, 13 point something weeks. Now, the interpretation of this interval is that for all the propellants which are aged 13.3625 weeks, their mean strength is between 2086 and 2176 with a 95% confidence. Yes.
I'm going to assume that the X naught is equal to.
It's where you are interested. It depends upon where are you interested. Where do you want to predict? Where do you want to estimate? Now, the comment about this specific part of the confidence interval, this part of the confidence interval. Now, if you look at the confidence interval as a whole formula, when is this confidence interval getting minimized? This confidence interval, obviously, what is the objective? At the end of the day, you want to minimize the confidence intervals width, right?
Yes.
How can you minimize? I'll tell you all the factors that can be used to minimize. The first thing to minimize is this constant, 2.101. If this constant is small, the width will be small. Now, how can you minimize this constant is by increasing the value of alpha. You can minimize this constant by two things. Number one, increasing the value of alpha. Number two, increasing the value of sample size. Because this constant is coming from t distribution, and when you put t distribution, you give two arguments, alpha and n minus 2, right? So if you increase n minus 2, this constant will go down. If you increase alpha, 1 minus alpha will come down, and this constant will come down. Impossible to do any of these two. You cannot afford to be less confident. Your objective is to be 95% confident. You cannot afford to be less confident. This is number one. You cannot afford to increase the sample size. So this is not a possibility. This is no longer a possibility. Then sigma square. This MSE is the variance of y. This is an estimate for the variance of y. You cannot play around. Whatever is the variance of y, it is the variance of y. You can't do anything about it. This is just an estimate of that variance. It is what it is. You can't do anything. The next factor is 1 over n. You can again minimize this if this 1 over n is minimum. 1 over n minimum or n is maximum. You cannot maximize n. You can't play with n again. You cannot increase n. The next factor is this SXX. There is SXX here. The next factor is this SXX. This SXX is a measure of the variance of x. You can't do anything about it. The only thing you can do about is this thing. If this thing is 0, this whole will vanish, right? And the interval will be minimized. True? When will this thing be 0? When x naught is x bar, or I will say it in words, when you are predicting close to the average of x. When you are predicting close to the average of x. There are certain levels of x, age 11, age 12, age 13, age 14, age 15, age 16, age 17, age 20. So this is the width of the ages. If you are predicting in the center of these ages, your prediction will be best. Variance will be minimized, intervals will be minimized. Can you really control this thing that you are predicting in the center of x? Somehow you can when x's are fixed. I'll tell you how. Let us say I gave you the objective that this is my x. You are the one who's going to design the study. This is my x. This is my y. X is the age of the propellant. Y is the strength of the propellant. You are the one who's going to design the study, right? And I tell you my final objective is this. I want this interval. That's my final objective. You decide what are the levels of x's you want to keep, and then you go test the propellants of those ages and get the strength and get the data. Right? This is the objective. What will you do? If I tell you at the start of the day that I want to predict for the age 15, I want to predict for 15 weeks old propellants. What will you do? You will select the propellants nicely and around 15. You will space the x's in such a way, because x's are the ones you are controlling. You are picking the propellants with specific ages. X's are fixed means you are the one controlling x's. So you will pick the propellants, you will set the ages in such a way that the end of the day where you're predicting comes in the center of the ones you are picking.
The average of the numbers that I chose is 15.
The average of x's you select should be close to where you are predicting, which is 15. So when you start your study, you take those data, you take those propellants, which are 11 years old, 12 years old, 13 years old, 14 years old, 15, 16, 17, 18, 19, 20. So 11 to 20, if you take it, the average is around 15, right? So for these propellants, you measure their strength from the data and run the model. So if the objective is in the mind from the start, if the final objective is in the mind from the start, you can decide about the spacing of x. This is called spacing of x. You are the one who's going to decide about the spacing of x. So the spacing of x should be chosen very carefully according to the end objective.
Now that sounds mathematically logical, but is it logical to predict the age of provenance aged 15 weeks by taking 11 to 20?
Most of the experiments, when you perform them, these are controlled experiments. By controlled experiment, I mean you are the one who's performing the experiment, and these experiments are like you put this much of chemical and then you see the reaction and you see how much of this is produced. So when you do perform the experiment, the input is what you are going to decide. X is called the input. Y is usually the output. So usually the input is what you are going to decide. So when you perform the experiment at different levels of input, you are specifying the amount of chemical to be input. So you decide about these levels of X's, the inputs, according to the end objective. Where do you want to predict? So let's say my X is chemical 1 and my Y is whatever is the amount of output produced. So at the end of the day, I want to predict at when chemical number 1 is 10 mg. So I will choose the spacing of X's in such a way that the average of X is somewhere close to where I want to predict.
If I take a smaller interval of spaces, will it give more accurate, still be the same?
No. Here is the reason. Let's hope I have a marker. When you the reason is here. When you have a smaller range of X, what will happen to this? Let's say you want to predict at 15 and your data is from 14.9 to 15.1, very restricted. What will happen to this? Suppose this is not exactly 0. What will happen to this? This is the amount of variation in X. This will be small. When this is small, what will happen to the interval? It will increase. So the spacing should be big enough and around the mean. Big enough and around X bar.
So you said that, you said 6X we cannot control.
The variation of X you can. The variation of X you can. Variation of Y you can. Variation of X you can. For example, you're performing the experiment. You can put the chemical all the way from 10 to 20. 10, 11, 12, 13, 14, 15, 16. You have to perform the experiment handily, right? So it's up to you. You want to choose the input to be 10, 11, 12 all the way up to 20, or you want to choose it 14.9, 14.92, 14.94, 14.96. It's up to you. If X naught is exactly X bar, the denominator doesn't matter. Because it's going to become 0 anyways. The denominator doesn't matter. But if this is not exactly 0 and it is close to 0, then the denominator also matters. Now, also from the practical point of view, you will always not be predicting close to X bar. You can be predicting right and left. So according to the practicality of your model, the bigger the width of X, more practical it is to report. It will be good to report that you can use this model from all the way 11 to 20, rather than saying to the user that you can only use this one if your X is between 14.99 and 15.01. Otherwise, you can't use this model. So a larger width of X makes the model more practical and more attractive to the user, because the user can use it for a bigger range of X's. This is what they are trying to explain probably in this paragraph. They are saying that note that the width of the confidence interval is a function of X naught. It is minimum when X naught is X bar and widens when this increases. Intuitively, this is reasonable, as we would expect our best estimate of Y to be. And I was going to make this line something like this. When you actually draw this confidence interval, when you actually draw this confidence interval, it looks like this. Suppose this is the line. This line is what? This line is the point estimate. This is actually the mu hat of y when x is x, right? This line is the point estimate. And when you draw the confidence interval around this line, let's say this point is x bar, the center of x, then the confidence interval, if you draw it, it comes like this. The width is its minimum at x bar. It's more precise or most precise when you are close to the average. We call this one as, I think, confidence band for the confidence interval of mu of y when x is x naught. Any question up to this point?
They say that this sample is random sample. It's no longer random.
No, it's still random. X is not random, but y is random. It is still random.
It's
X's are fixed. Yes.
What's between mu hat y given x and y hat?
And I'll talk about this. I was going to talk about this. Yes.
What's the ideal number of pixels? This will not be costly for the research.
There is no ideal number. There is no condition on number of levels. There is no condition on that one. You see in the formula, there is the number of levels is not there. There's only SXX, which is the amount of variation in X, which will positively affect the interval if the amount of variation is more. And then there is X naught. Then there is X naught, which means that you should be predicting close to the average. Whatever are the levels of X's, you should be predicting close to the average. What happened? Close to the average. It's not always possible to be exactly on the average, but close to the average.
To research about like 20 x equal 20. Do you want it was between 15 to 25 or from 10 to 30?
It depends where the data is available. More variation is better. More variation is better. 10 to 30 is much better than 15 to 25, if it is possible. At the end of the day, there is also a question of possibility. Do you really have the data from 10 to 30?
Is it worth it?
It's work. It's work. But again, does your variable practically has values from 10 to 30? Right? Maybe your variable is the score of the student. So of course, it's better to have the data on score of students from -100 to +200. But is it possible for a student to have -100 score? So you have to see the possibility of the variable. Can it really go that far? So there should be a natural width of X. So it is best to cover all of it. You cannot go beyond.
Yes, you said that the x is not fixed.
We are assuming X's are fixed.
You mean X or X bar?
If X's are fixed, X bar is also fixed.
And the mean of the expected value of X bar would be
Everything is fixed. We are talking about this thing. X naught, where we want to predict. We should fit it somewhere close to X bar, which is fixed, of course.
Spacing.
No, you are not going to change that. Suppose you are going to pick 10 units. Suppose you are going to pick 10 units. Those 10 units can be choice number 1. Those 10 units can be 10, 11, 12, 13, 14, 15, 17, 18, 19, 10 units. And you can also pick those 10 units as 14.6, 14.7, 14.8, 14.9, 15.0, 15.1, 15.2, 15.3, 15.4. Same 10 units.
Can't do it from the
Sample. This is for the sample. Yes, this is for the sample. 10 units. So you fix, in case number one, you fix 10, 11, 12, all the way up to 20 as the levels of x's. In example two, you fix from 14.5 to 15.5 as 10 levels of x's. Now, for both cases, n is 10. But for the first case, there is more variation. Sxx will be more. For the second case, Sxx will be small. So this interval will be wider for the second case.
You can't change the way you.
Yeah, that's what I was talking about. At the start of the study, you are the one who's going to, not you, the experimenter is the one who's going to decide about the levels of x's. At which levels should I perform the experiment? Any other question? No questions? Plus, I will see you inshallah after vacations. I was expecting some of you to. I was expecting some of you to request for no class today, but nobody asked.
We can request for
Sunday.
Sunday after the class, I will say the same.